Hello, and welcome to lesson 15 of this Introduction to Linear Algebra with Wolfram U. The topic for the lesson is eigenvectors and eigenvalues. So let's begin with a brief overview of the lesson. So let's say you have a square matrix, a square n by n matrix, n rows and columns. Then associated with A are special numbers or values really, and special vectors. And these special values and vectors are called eigenvalues and eigenvectors for A respectively. So you can think of them as being kind of belonging to A, very peculiar and special to A itself. Now, why these are important? Because they help to break down the linear transformation associated with A into simpler elements. And of course, if you look at various applications in the real world, you'll find that eigenvalues and eigenfunctions appear all the time. So let's begin with a motivating example. So here you have a matrix A and a vector V. So vector V is 5, 1. And if you do A dot V, you get 15, 3, which is 3 times the original vector. So A times V is 3 times V. And thus, what the matrix A does over here is it stretches the vector V by a factor of 3. So in such a case, we say that the number lambda equal to 3 is an eigenvalue of A, and that's the eigenvector. Okay, now if you take another vector like negative 3, and you try the same thing, you find now that you actually don't get a multiple of the original vector, and so this vector u is of course not an eigenvector for A. So here's a plot which shows that the vector v is stretched by A, but something different happens with u. So you have an eigenvector over there, but not over here. Okay, so now formal definition. So if you have a square matrix A, then an eigenvector is a vector such that A times V is lambda times V for some scalar lambda. And the scalar is called an eigenvalue, and the vector V is called an eigenvector. Okay, and the set of all these eigenvector eigenvalues together give you the eigensystem for A. So as an example, here is a 2 by 2 matrix A. You're trying to show that 2 is an eigenvalue of the matrix, and then you want to find the corresponding eigenvector to do that. So basically, you need to solve the equation A times V equal to 2V, which can be written as A minus 2 times the identity matrix times V equals 0. And we have a nice function called null space, which will do that for you. So you do A minus 2 times identity matrix 2, and you get back negative 1, 3. So the vector V in this case is an eigenvector. Let's check that. So you get back A times V is 2 times V. Okay, now of course you have an eigenvector, then any multiple of it will also be an eigenvector. Example 2, let's say you have number 3, and let's try and show this number 3 is an eigenvalue of the matrix over here by finding the corresponding eigenvector. So again, you need to solve the equation AV equal to 3V, use null space, you get back the answer 0, 0, 1, which you might have guessed from the last column over here. So the vector 0, 0, 1 is an eigenvector for this matrix. Let's check that, and you do see that it is an eigenvector. So the eigenvalue is 3, and the eigenvector is the vector 0, 0, 1. Okay, so now, luckily, the Wolfram language has some very nice functions for computing eigenvalues, eigenvectors, and in fact the entire eigensystem for any matrix. So here's a matrix A. You can work out its eigenvalues with the eigenvalues function. You can work out the eigenvectors with the eigenvectors function. So you have 3 eigenvalues and 3 eigenvectors, and you can work out the entire eigensystem with the eigenvalues over here and the eigenvectors over there in one go. Now, of course, question is, how does one find the eigenvalues? Well, we learn in the next lesson where we'll talk about solving a polynomial equation to find the eigenvalues. And now, of course, once you know the eigenvalues, you can work out the eigenvectors quite easily. Okay, so now let's talk about eigenspaces. You see, so if you have an eigenvalue, then of course, by definition, you have this equation over here being satisfied for some non-trivial, non-zero way. Now, this is a homogeneous equation. The right-hand side is 0, so you have potentially many solutions, and the set of all these solutions is called the eigenspace of A, corresponding to the particular value lambda. And of course, 0 is always a solution, so in fact, we'll think of 0 as belonging to the eigenspace as well, along with all the eigenvectors corresponding to lambda. Okay, so as an example, here is a 3 by 3 matrix A. Work out the eigenvalues. You see there are only 2 distinct eigenvalues, but there are 3 distinct eigenvectors, and the first 2 over here in the list, v1, v2, so v1 is the first one, v2 is the second one, they actually belong to the eigenvalue 4. Now, of course, if you take any linear combination of those, it is again an eigenvector. And the third eigenvector over here belongs to the eigenvalue 1. So that's the idea of computing the eigenspaces for eigenvalues. Now, the nice thing about eigenvalues and eigenvectors is that if you have eigenvectors that correspond to distinct or different eigenvalues, then they're actually linearly independent. So here is a matrix A. It has 3 distinct eigenvalues 8, 4, and 3. There are 3 distinct eigenvectors, and what you can do is you can simply work out the determinant of the matrix formed by the eigenvectors. You see it's not 0, so hence you have linear independence for these eigenvectors corresponding to distinct eigenvalues. And finally, let's talk about triangular matrices, which are really simple. So if you have a triangular matrix, then the eigenvalues of this matrix are the entries on its leading diagonal. So here is an upper triangular matrix. You see the lower triangle elements are all 0, and the eigenvalues over here are just the sorted diagonal elements from here. So you got 1, 29, 61, and 43. And let's say you have a lower triangular matrix over here, then its eigenvalues are again the sorted elements from the diagonal over here. So triangular matrices are simple. You can work out the eigenvalues simply by looking at the diagonal elements in each case. Okay, so that brings me to the end of the lesson, and the point is that given a square matrix, you can talk about its eigenvalues and eigenvectors, and given any eigenvalue, you actually have an eigenspace of vectors associated with it. Now, if you have eigenvectors corresponding to distinct eigenvalues, then they are linearly independent. And if you have a triangular matrix, then fortunately the eigenvalues are simply the entries on the leading diagonal. Now, to automate all the calculations, you can use eigenvalues, eigenvectors, eigensystem in the Wolfram language to do all the computations area. These are very efficient functions, so I advise you to use them whenever possible. So that's the end of this lesson, and next lesson we talk about characteristic equations which can be used to find the eigenvalues, but that's for the next time, and I'll stop over here. Thank you very much.